Okay, so welcome back to another video. Today's video is going to be a nice little double integral computation, both on the variables of x and y ranges from the positive reals, from 0 to infinity, and what we have as our integrand is 1 divided by 1 plus x times 1 plus y plus x plus y, followed with dx and dy. So this is kind of interesting since usually when you want to tackle double integrals, iterated integrals specifically, that you want to tackle what's in the variable first, so dx, so that means you have to, of course, take this in respect to x, and then afterwards evaluate your bounds from there. Then you're just left with just the variable y, and then you evaluate that integral in respect to y to actually get the value of that integral. We're going to do something a little bit different. This is actually, I think, is an interesting approach that, of course, u-subs can apply. It definitely applies to what we're actually going to be working with, but we're actually going to be doing a u-sub into both of our variables before actually doing the whole double integral computation. And of course, change of variables, we're going to get different variables. It's going to simplify some things. And there's actually a nice expansion of a sum series that it's going to be utilized at the end, and it actually comes out to a very nice value, which has the pi in it. So, that's something interesting out of that. So with that out of the way, why don't we actually just jump right in? So for our variables, I'm going to let a be simply our 1 divided by 1 plus x. So 1 divided by 1 plus x. Now, if I were to solve this for x by itself, I have x, and then that's set that equal to 1 divided by a, and then subtract 1. And if I want to differentiate both sides, I have that dx is going to equal to negative 1 divided by a squared, and then dA. We can do the same thing here. So we let b, now we let that be 1 divided by 1 plus y. Then that means if I solve for y on its own, then it's just going to be the same, argument as the above. That's going to be 1 divided by b and then subtract 1. And so differentiate both sides. So dy is going to equal to negative 1 divided by b squared with respect to b db. Okay, now let's actually put this back into our substitution. And so we have our new bounds that we need to change. So first off, if I plug 0 to infinity, so for y, that will be the b variable we're looking at. So that means our new b is actually going to range from 1 and then 0. And of course, that's going to be the same thing for a as well. So that means I have 1 to 0. Plug this back into the substitution. So I have that this is negative 1 divided by a squared, and the substitution for dA multiplied with negative 1 divided by b squared, and then dB. And then of course, what we have is that if you simplify some stuff out, not only that I have a 1 plus x, so that means, of course, that's actually simply just going to be 1 divided by a. Well, also a times b, since we simplified that from the top. So a times b, but actually 1 plus x. So what that implies is that I actually just plug this back in for back over here. And so what we have is going to be 1 divided by a, and then add this with 1 divided by b, and then plug this for x and plus y. And so we get that this is actually going to be minus 2. Okay, so that actually, we can simplify some things here. So let's actually switch to a different marker for this. I'll put this in black. What it actually comes down to, so after all that simplifying, is that this is going to reduce down to just, so our double integral from 0 to 1. And so what's left is we have dA and then dB, all this being divided by a plus b, and then subtract 2 times a times b. And so what we can do here is actually, this is actually utilizing Fubini's theorem such that we can actually split the integrals up as like it's a product. So what we have is that this is 0 to 1, and we're actually going to separate this for dA over here, and then multiply with the double integral from 0 to 1 of dB, and then this is being divided by, so b, and then subtract. So I actually just factor out the b from this term over here, so 1 subtract 2a, and then add this with a. So what we can do here is that I'm actually just going to skip a step here, but what you would want to do is you have to apply a u-substitution over here. And what that comes down to is that the antiderivative is going to be in terms of a natural log function. So from 0 to 1, so this is still dA over here, then multiply by, so that means after computing the antiderivative, what we're going to have is that we're actually using the substitution for u equals the denominator, and then you actually want to integrate this in respect to b. And so what that comes down to is that we have the natural log of b, then multiply by 1 minus 2a, and then add this with a, and then all being divided by 1 minus 2a. We evaluate this from 0 to 1 over here. Okay, and that's pretty standard to see that this is, of course, if you plug in 0 for all of this, you're gonna get that everything's gonna be 0. And then what's left is that, so that means I have the new integral, so 0, 1, and then dA. And then over here, what this evaluates to, so I have that this is gonna be, so of course I have a 1 minus 2a, so let me actually write that at dA, and then divide it by 1 minus 2a. And then plug in 1 over here for b, so that means what I have now is that this is actually gonna be just ln of 1 subtract a, and then subtract ln of a. We can actually utilize the natural log properties to reduce things even further. So I have now the integral from 0 to 1 of just ln of 1 subtract a, and then divided by a, and then multiply. So we have a dA, and then divided by 1 minus 2a over here. This looks a little complicated from here now, but don't worry. U-sub is actually, yet again, our friend that we will be utilizing to help make things a little simpler from here. So we'll let u equals 1 minus 2a, and then what we have is that I'm actually gonna solve for a by itself. So that means I have that, or rather I'm gonna have 2a. So that means I have 2a is gonna equal to, 1 minus u. Then we can actually just differentiate both sides over here. So I have that 2, and then dA is gonna just equal to negative du. So in other words, that's just gonna be that dA is equal to negative 1/2 and then du. Okay, so we'll plug this back in, and really I should have called this capital I from the very beginning. So let's capital I is this entire thing. So let me actually put the equals to denote this over here. So we have the new substitution, and then we have to evaluate our bounds too. So 0. Okay, so if I plug in 0 for a, so that means our new lower bound is going to be just, positive 1. And if I plug in 1 back here, so that means that's going to be a negative 1. So negative 1, 1, already know that if we have to switch the bounds, we're going to get a negative integral out of that. So now I'll just plug in everything. So I have ln, and then what we have 1 minus a. So of course I just solve for, a by itself. So divided by 2. So what we have that is going to be 1 subtract, and then right here 1 minus u divided by 2. All this being divided by, so a, and then solve for that. So it's 1 minus u divided by 2 over here. Okay, and then now just substitute the dA differentiation as substitution. So I have negative 1/2 and then dA, and then all this being divided by, so we said that 1 minus 2a is going to be u over here. Okay, and so we can actually simplify things out even more. So for 1/2 can be factored out. I have to change the bounds of integration. We have a negative number as the top, and then the positive one's bigger than the other, so we have to switch that. That cancels out that negative sign, thankfully. So that means I have a 1/2 out here, and then our integral is going to be from -1 to +1. And then, so we actually just simplify some things over here. So I could actually just multiply a 2 just to get rid of the denominator from both the fractions from both numerator and denominator. And then we just simplify that out. I have, this is going to be, so ln of 1 plus u, and then divided by 1 minus u, and then du, and then divided by u. What's great is that I have I is equal to this. So therefore, the conclusion so far we have reached to is that 2 times I is going to equal to the integral from -1 to 1 of ln of 1 plus u divided by 1 minus u multiplied by du divided by u. And what we can do here is let's actually split up our bounds. So that means what I have is I'll actually split this from -1 to 0, and then from 0 to 1. So -1, 0 of the natural log of 1 plus u divided by 1 minus u, then du divided by u, and then add this with the integral from 0 to 1 of our same integrand over here. And so what we're going to do is we're actually going to just focus specifically on this integral over here and apply a nice little u-substitution yet again. So what I'll do is we're going to actually let u equals -t in this situation. So right here, u equals -t. And so that means that du is going to equal -dt. And so what that means is that now our new integral over here is going to be the following. So what I have is now the integral from, now we actually change our bounds. So that means what we have is that this is going to be from 1 and then 0 of ln of 1 minus t, and then divided by 1 plus t. Then -dt divided by -t. So what that reduces to, of course, is that the negatives will not only cancel, we have to switch our bounds. So that because the 1 and 0, so that becomes negative, and because the negative is associated with the natural log signs, We can use properties to actually move that back into our input, and then that's the exponent, aka we can actually just flip the reciprocal. And so what that means is that this actually comes into a similar fashion that we actually have double the integral. So in other words, back into over here. So let me actually reduce this to say, so we have 0 to 1, and then ln of, 1 plus t, and then divided by 1 minus t, then dt divided by t, dummy variable, of course, so that means this is actually shared the same thing. So literally, it's just the same thing as 2 times the integral from 0 to 1 of the natural log of 1 plus u, and then 1 minus u, then du divided by u. And so continuing further from here is that what we're going to do is, what's nice is that I'm actually going to use a nice Taylor series expansion for the ln, the natural log of 1 plus u, and the natural log of 1 minus u. And it also verifies that because our bounds are from 0 to 1, and it's actually convergent for those both Taylor series that they have to be the absolute value of x is strictly less than 1. So I'm actually just going to erase this side over here so we can actually continue on with the work. And to reiterate what our Taylor series is, so the two of them we'll be using is that the natural log of 1 plus x is simply just going to equal to the infinite sum. So for our index n is equal to 1 of this -1, and then to the power n plus 1 multiplied by x to the power n, and then divided by n. And then the other one is going to be the natural log. So we'll actually write a negative actually. So negative natural log of 1 subtract x, which is going to be the infinite sum over here at n is equal 1 of x to the power n, and then divided by n. So of course, both of these have the absolute value of x is strictly less than 1, which that satisfied that. So to put everything back in together, back into over here, so that means I, and well, I actually say that 2i is going to equal to 2 times that. So let me actually move that back in. So over here, so we have the integral from 0 to 1, and then it's going to be 2 times. And so what it is the natural log of 1 plus u, and then applying those rules against division. So natural log of 1 plus u minus natural log of 1 minus u. And then what we do is that following with that expansion, if you just combine everything together, what we have is that the following, and also distribute the 1 divided by u back into inside that expansion, and you're going to have some terms that cancel. You're going to have that this is going to be 2 times, so 1 plus 1 over 3 times u square, plus 1 over 5 u to the power 4 plus 1 over 7 u to the power 6, and then so on and so forth. And then that's going to be in terms of du. And so what we can do is now the antiderivative is kind of easy. It's just term by term yet again. So it's actually carries on forever and ever. So it's going to be 2 times. So antiderivative of each I have is u, and then plus u cubed divided by 3 square, then plus u to the power 5 divided by 5 square, plus u to the power 7, and divided by 7 square, plus so on and so forth. And if we evaluate this from our bounds to 0 to 1, and of course that this is going to reduce to everything for 0 is just going to disappear. And so if I plug in 1, so I have this is going to be 2 times. So this is going to be 1, and then plus 1 over 3 square, plus 1 over 5 square, plus 1 over 7 square, plus so on and so forth. And this is actually nice that it actually comes down to a result of just pi squared divided by a. A nice little proof is such that you just need to utilize Basel's problem, which is pi squared divided by 6. Then what you can do from there is you multiply 1 over 4 to that value of Basel's problem, rewrite the 4 as 2 square, and if you actually perform the multiplication out and then use that the series expansion of zeta of 2, then if you actually subtract pi squared divided by, or pi squared divided by 6 minus pi squared divided by 24, you'll get pi squared divided by 8, and then you're gonna have those even terms cancel out from that series expansion such that you're only just left with just the odd denominators over here, square. And so that actually just leads up to that and say that the final answer indeed is just gonna be, so 2 and then times pi squared divided by 8, which of course reduces to just pi squared divided by 4. And that is indeed our final answer to this nice little double integral, utilizing a whole bunch of u-substitution. And then as mentioned, we actually did use two of the Maclaurin series expansions to reduce this down nice and clean. So yeah, there you have it. And that's pretty cool if you ask me.